So I'd like you to think about the difference between developing productive ways of thinking versus just focusing on answer getting. If the focus is on answer getting alone, then instruction becomes sort of like a mimicking process. Hey, students, let me show you how you can get the right answer, and just practice and practice and practice and practice until you can do this thing to get the right answer every time. Now, I'm not saying that getting right answers is not important. It absolutely is. But in addition to that, combined with that, is the ways of thinking that help students to flexibly and fluently arrive at those good answers. I want to use this division as the context to make my point. So you watched a video from Math Cuts where in this video you saw lots of different ways to divide. You probably could distinguish between how many groups, how many in each group, the idea of what division means and how you engage in it. But then how you follow the algorithm thinking about what division means is what I want to focus on here today. Let's do it in the context of your exam question. This was the exam question where a dollar is 112 yen. You pay 1920 yen for a dinner. How much will you be reimbursed in US dollars? And so the question here, the thinking first of all was how many 112s, how many groups of 112 are in 1920? Because every group of 112 constitutes one US dollar. So from the reimbursement stage, what we have to figure out here, what the conversion would have to figure out is how many 112s, how many $1 are in 1920. That's how many $1 I would be reimbursed. And that's a division question. So first of all, just knowing that we should divide is an important part of the development of ways of thinking. So often students get a question like this and they go, oh, am I supposed to multiply? Am I supposed to add? Am I supposed to subtract? Am I supposed to divide? And they just throw out all the possibilities until they get the thumbs up to do what they're supposed to do. Part of the ways of thinking is thinking about what should be done and knowing why you should do it. So dividing is the right thing to do. Now, let's be honest. If you're going to divide 1,920 divided by 112, you're probably going to grab your phone, or if you're old school, you're going to grab a calculator, and you're going to do the division. But I argue that just knowing that you should divide is an important part of this. But then let's suppose you're in the probably fourth to sixth grade area in mathematics, and we're teaching students to divide by hand. And so it would look like this, traditionally speaking. Students will be told, well, you're dividing, so the 112 goes outside the box, and the 1920 goes inside the box. And students often go, well, how do you know which one should go inside and outside? And that's part of the issue. And we have to get students thinking about what we're trying to accomplish here in doing this. How many groups of 112 are contained in 1920? That's the question. All right, now, in the traditional sense, here's how it might sound. This is based on my many, many, many years of experience hearing teachers and students work on things like this, but they would say something like this. Well, first, how many times does 112 go into 1? Not. It doesn't. 112 can't go into 1. So then how many times does 112 go into 19? Oh, you can't put 112 into 19. How many times does 112 go into 192? Oh, that one we can do. It goes in one time. And then you multiply. 1 times 112 is 112. And then you subtract and you get 8, 0, and then you bring down the 0. And then you say, how many times does 112 go into 800? Well, it turns out you can do it 7 times. Now, this would take some time probably for students. Is it twice, 3, 4, 5, 6? Let's try it. Yes, 7 works. And then you would multiply 7 times 112. I'm going to grab my calculator on that one, but perhaps if you were in elementary, depending on the context, you might not use calculators. You might, I don't know. But 112 times 7 is 784. And you once again subtract and you get 16. And now you have to put a decimal and another 0 and you bring down the All right, let me just pause there for a minute. The reason some of you got some comments from me about this is, what are the ways of thinking about mathematics that we're cultivating in an approach like this? I say very little, or at least not good ways of thinking about mathematics. Let's go back to the beginning and let me unpack why I say not good. All right, in the first case, back. Okay, in the first case, if you guys, maybe you don't know this, maybe you do, but I've heard it a million times. How many times does 112 go into 1? It doesn't. Okay, first of all, that's not a 1. That's a 1,000. And we're treating it like a 1. So that's mathematically inaccurate to say how many times does 112 go into 1, or how many times does 112 go into 19, or even how many times does 112 go into 192. None of those are right. The 1 is a 1,000, the 9 is a 900, the 2 is a 20. So none of this is mathematically sound. So I don't want our students thinking in ways that are not mathematically sound. I want them to develop productive, mathematically accurate and precise ways of thinking that are productive and can help them to maneuver forward to get correct answers. All right, second of all, let's say I don't know what I was just doing there. Second of all, I can't put it back, dang it. When we did that first move and we put a 1 up here and you did 1 times 112 is 112, and then you subtracted. Now look, it's not 192 minus 112, and it's really not even a 1. What you're really saying in this moment is, let me put it over here. In that moment, what you're saying is 112, you can take 10 groups of 112 and get 1, 1, 2, 0. At least 10 groups of 112 can be taken away from the 1920. So at least 10 US dollars are going to be needed to reimburse this meal. At least. So look, when you do it over here and we say a 1, 112, 100, we're not doing it right. We're really saying 1, and notice it's in the tens place. That's not a 1, that's a 10. And then when you subtract and get 80, and then you bring down, okay, this is another thing. What does that mathematically mean? What is the mathematics behind bringing down a 0? I will argue that in the mind of students, and maybe many teachers, there is no mathematical meaning. It's just a way to get the right answer. You bring down the 0. But look over here. What's really happening is when you bring down the 0, you're saying you subtracted and got 80, but it's really not 80. It's 1920 minus 1120, which is 800. When you so-called bring down the 0, you're finally paying attention to place value and getting that 800. But do you see what I'm getting at here? The style on the left ignores the mathematics of place value, ignores the mathematics of what division means, and ignores the mathematics of keeping track of that how many 112s are in 1920. It's not a 1 into 192, it's a 10 into 1920. And so we're just trying to find other ways to approach this that are more mathematically sound and focuses on good mathematical thinking, which place value is part of. So if we continued it over here, we now have, the thinking is 10 groups of 112 fit into 800. I need some more. And this is where you wouldn't have to be the most efficient. A fourth grader is not going to be the most efficient necessarily. So they might go, well, I think I could probably do 4 more. I'm just making that up. 4 more. 4 112s is 448. So for sure you can take out another 4 groups of 112. And 800 minus 448, I think that's going to be 352. And then maybe at this point you say, well, I think I can get 3 more. I didn't do this very well, but I can get 3 more. That would be 336. And 336, I think that's going to give me a 16. All right, so look up here. I took out 10 groups of 112. I took out 4 more groups. I took out 3 more groups, and I'm just taking out groups of 112 is my thinking, and I can do this more or less efficiently. I may have done 10 and then 7, or hey, if I was really efficient, I would have just taken out all 17 groups of 112 that I could have taken out. But that's the problem. Students sometimes in this world where you're looking for the most efficient way, they're stuck. And they go, oh, I don't know what to do here. I don't know what number to put. Put anything you want. I didn't have to start with 10. I could have started with 2 or 5 or 7. I could have started with anything and then just keep taking out groups of 112 until I can't take out any more, and now I can't take out any more. But this is where we have to also be thoughtful. There's a remainder of 16. So all of this adds up to 17. So 17 groups of 112 yen, that is 17 US dollars, are going to be reimbursed. But then there's an additional remainder here of 16. So here's the thinking. How many groups of 112 are in 16? There's not one whole group of 112, not even a half of a group. I mean, think about a half of a group of 112. Half of 112 is 56. It's not even a half of a group of 112 in 16. Is it a fourth? Is it a tenth? We could start taking out tenths and see what if we took out a tenth of a group of 112? A tenth of 112 would be 11.2. So I could do that. I could take out a tenth of 11.2. That would give me, I think that's a 4.8. I'm down to 4.8 now. And then I keep going. Now I can't even take out dimes. Remember, a tenth of a dollar would be dime. I can't even take out dimes anymore. I probably have to go to pennies. How many 1/100ths? How many 1/100ths of 112 are in? It's 4 would do pretty well here, at least rounding. 4 100ths now. 0.04 would be just about getting me close to that 4.8. So it turns out to be 17 full 112 yens, a tenth of 112 yen, and 4 100ths of 112 yen. And it came out to be 17.14. But here's my point. I really want you to take away is this. When we do things like this, the traditional way, just to plant a seed, I like to say, put a pebble in your shoe. Think about the things that you do, and are they grounded in mathematical thinking, or are they grounded in just trying to help kids get the right answer? Now, I say that kind of sarcastically because I want to make the point that while getting the right answer is good, so is good sound mathematical thinking. Let's be honest. In the real world, you're not going to go through this in terms of an algorithm with paper and pencil. You're going to grab a calculator or ask Siri and probably have some conversion chart, convert yen to dollars. But don't we want humans to understand that when they do the conversion and they get $17.14, you might actually go, oh, well, that makes sense that it would be about 1,712s are in 1920, 1,120. We want the thinking in addition to the answer getting. Hope all that makes sense.